Okay, Assalamualaikum and hi. So for this week, what you're going to learn is about the chapter number 3, which is the introduction to chemical reactor design. Okay, before this, for topic number 1, you learn about introduction to chemical reaction in engineering. But for this topic, you will learn more how to calculate certain values such as the concentration, the flow rate, and also the volume of the reactor. Okay, so for the lecture outline, what you're going to learn is the first one is the relation between the concentration and conversion. You have to relate between the C and also the X. Okay, so we will have a batch system basically and also a flow system. Okay, whereby these two we can calculate the C, alright, but in the different terms. Okay, for example, for batch, we are looking at the number of the moles, and the flow, we are looking at the F, alright, which is a mole per second. Okay, and then what you need to learn is how to construct a stochometric table. Okay, so you have to know what are the columns involved. Alright, so each of the column have a different value. Okay, and at the end of the chapter you will learn about the material balance for the batch reactor, CSTR and PFR. Okay, so material balance is very important before proceed to the topic number 4. Okay, so how we relate between the concentration and also the conversions. Okay, so let me refresh you back from the topic number 1, okay, or the topic number, topic number 2, whereby the number of moles of a chemical species I that have reacted per mole of I fed to the system. Okay, so we have a Xi is equal to mole of I reacted over with the moles of I fed. Alright, means that we have a Xe is equals to reacted, so we need to know what is the difference between the Na naught minus with the Na, alright, over with the Na naught. Alright, so let's say this is a batch system whereby the volume would be the same. Alright, V is equals to V naught. Alright, so what you can do is you divide all this with the V. Okay, so this one cancel will be 1. Alright, so you expand the equation, become 1 minus with the Na over with the V, and then Na naught over with V. Okay, so from here you can simplify it into a concentration equation, which is the Xa equals to 1 minus with the Ca over Ca naught. Okay, so from here you can rearrange it, become Ca is equals to Ca naught 1 minus X. Okay, so the concentration of any T, alright, is equals to the initial concentration times with the 1 minus with the conversion. Alright, this one you need to change it from the percentage into let's say there 90%, means that you need to make it as 0.9. Okay, we move on to the important part, which is the stochometric table. Okay, so what is stochometric table? So it is used to present stochometric relationship between reacting molecules for a single reaction. So let's say we have a single reaction involve E plus B is equal to C plus D. Okay, so the small letter here actually is referring to the stoichiometric coefficient. Okay, recall from topic number 1 that we've learned negative RE is equal to A equal to negative RB is equal to over with B is equal to RC over C is equal to RD over D. This is how you relate with all the molecules involved in the single reaction. Make sure you have the correct value, which is for RA, RB should be negative, and RC and RD should be in a positive. Alright, if A is limiting reactant, basis of calculation is taken as per mole of A, means that you need to divide B, C and D with the small letter of A, okay, and becoming like this. Okay, make sure this one stand alone. Alright, so next we develop the stoichiometric relationship for species in the reaction that we show as changes in mole for each species. We do this by constructing stoichiometric table. Okay, so for stoichiometric table we have two kind of category, which is the batch system as well as the flow system. Okay, so this one is applicable for fluid ataupun we call as liquid, and also gas system. Okay, so for example, batch system is we are looking at the number of moles. Okay, and for the flow system we have flow, we call it molar per second. Okay, this one is number of mole. Okay, so basically what we do is we need to get the concentration. Okay, alright, so which is the C. So how we get the concentration is by N will divide with the V here, alright, the volume, and this one is F will divide with the volumetric flow rate. Okay, alright, see this is the unit would be mole over with the liter, or it can be ataupun it can be decimeter cube and so on. Okay, and this one F would be mole over second, and volumetric flow rate is liter or decimeter cube per second. Okay, so you will have a same concentration unit, which is mole over liter. Alright, okay, so stoichiometric table for batch system. Okay, let's see, we have a reaction here in a reactor whereby at T0, alright, this is the initial value for A, B and inert. Okay, so inert, there is no reaction for inert, okay, but it present in the reaction. Okay, so that's why if you can see there also a Ni for the outlet. Okay, this is the outlet and this is inlet. Okay, so Na naught is the number of mole of A initially present in the reactor. Okay, so this is at time 0. Okay, for the feeding, alright, into the reactor. And then we have a Na naught X, moles of A are consumed as a result of the chemical reactions. Alright, so this Na naught X actually is what being consumed here atau being reacted. Alright, and then we have a Na naught minus Na naught X, moles of A leave or remains in the system. Okay, so after at any time, okay, the process complete, and what remains here will leave in the system. Okay, so Na, okay, which is after T, at any T, alright, is equals to the initial one, alright, minus with the Na naught X. Okay, the one that being consumed. Alright, so this is the complete calculation for Na. Okay, same like the one that in the introduction in this topic, whereby I've derived the equation for Ca is equal to Ca naught 1 minus X. Okay, this is how you get lah. Alright, but in terms of the number of moles, we want to determine the number of moles of species B remaining at time T after Na naught X moles of A have reacted. For every mole of A that reacts, B over A moles of B must react. Okay, so how to know the moles B reacted? Actually, you have to relate with the moles of A reacted. Remember, A is a limiting reactant. Okay, so this one will be used as a baseline. Okay, so the moles of B reacted is B over A times with the Na naught X. Okay, so for the moles of A reacted is a Na naught X. Okay, this is for A. Okay, for B is equals to B over A times Na naught X. Okay, so how do you get the complete equation for the NB? Okay, the NB which release here or remain here, same just like the batch kan. Okay, so NB is equals to the initial one, NB naught, minus with the B over A and A naught X. Okay, so this is the initial condition, minus with the moles of A reacted, then we will have the number of moles for the B molecules leave or remain in the system. Alright, for C molecules, you will have NC is equal to NC naught, the initial one, plus with the C over A and A naught X. Alright, which is the most A reacted. Okay, this one is the most C reacted over the most A reacted. Okay, and then we have a ND is equals to ND naught plus with the D over A and A naught X. Okay, this will be the for the D compounds lah. Okay, so to determine the number of mole of each species remaining after N naught X moles of A have reacted, we form the Stochometric table. Okay, so we put it into a table to have a clear view. So for the first column is for the particular species. Okay, we have A, B, C, and D, and also the inert. Okay, and then for the column number 2 is the number of mole of each species initially present. Okay, which is at T is equal to 0. Alright, that's why we have a Na naught, Nb naught, Nc naught, Nd naught, and Ni naught. Okay. For the column 3, they change the number of mole brought about by the directions. Okay, so this would be this third column. If you can see, minus Na naught X, and then for the B is minus B over A times with the Na naught X, and so on. Okay, but for the inert case, alright, there is no reaction occurs. Okay, and the last column would be the remaining one. Okay, whereby you combine the initially and also the change. Alright, okay, so you have a Na is equals to Na naught minus with the Na naught X. For the Nb, we have a equals to Nb naught minus with the B over B A Na naught X. Okay, but for the inert, alright, it would be the same as the initial one, which is Ni is equal to Ni naught. Okay, so the Nt naught would be the summation of the Na naught plus Nb naught plus Nc naught plus Nd naught plus Ni naught. Okay, and this is for the remaining, the total number of moles is equal to N, okay, I naught here, okay, plus with this part. Okay, alright, sebab Ni naught is equal this one, sama je. Okay, and then plus the rest of this lah. Okay, so this column initially is at T equal to 0, and this one remaining is T is equals to Nt. Okay, which is remaining is equals to initial plus change. Alright, so this one, if you remember the diagram for the reactor, okay, for this one is T is equal to 0, and then T here is equal to N time. Okay, so for here, this T equal to 0 is only involved for species A and B. Alright, at T0, there is no formation of C compound and D. Okay, so this would be 0 actually. Okay, same as this one. This one should be 0. Okay, alright. Okay, so from the total number of mole in the system, which is the NT, okay, we want to simplify this equation, okay, which this one will represent with del. Okay, so we will have nt naught plus with the del and a naught times x, which equals to nt. Alright, so del here is defined as change in the total number of moles over with the mole of a reactant. Okay, so let's say we have a 2a, alright, is equals to what do you call it, b, and plus with the 3c. Okay, so what is the value of the del here? Alright, del should be equals to, alright, we have a b here. Okay, so b will equals to this one. Oh, sorry, we'll divide with this one. Okay, with a small calculator, which is 2. Alright, so we have 1 over 2. Alright, and then we have a 1 plus with this one, 3 over 2. Okay, and then minus with 1. Okay, because this one is actually a over a. Okay, so it should be 1 minus 1. Okay, so you just do the calculation here lah, and you will get the value of del. Okay, okay, now for the constant volume batch. Okay, remember this is a constant volume batch. Okay, we have this v is equals to v naught. Okay, so remember here, this is for the incompressible quantity. Okay, the incompressible quantity. Okay, that is why the volume would be the same at t0 and at any t. Okay, so remember, as I told you, what we want to do is to convert the number of moles into concentration unit. Okay, because usually the value will be given in terms of concentration rather than the number of moles. Okay, so from here, remember this is the one that we obtain from the Stochometric tables. Okay, if you can see for the CA, you can convert it NA naught over V into a CA. Alright, so CA is equals to, right, sorry, this should be CA naught, NA over V is equals to CA naught 1 minus X. Okay, right, that's the what do you call it, the ultimate aim is to convert into the concentration. Okay, but for B, C, and D, alright, what we need to do is, now we want to change it into one terms only. Alright, so this one you will be introduced to a new symbol, which is a theta. Okay, so theta I is equals to n I naught over with the n a naught. Alright, okay, this theta is a unit list, so it not only can be become from the n number of mole, it also can have in terms of the concentration, alright, or in terms of the fraction composition. Okay, y I naught over with the y a naught. Okay, so for this part we focus on this one, number of moles. Okay, so let's say for B component, it will become theta B is equals to n B naught over with the n a naught. Another one, we have a theta C is equal to n C naught over n a naught, and then we have a theta D n C naught over n a naught. Okay, so we have to transform this n b naught in terms of theta b in order for easier for you to convert into into a concentration. Okay, so how we do it? Okay, let's look at the next slide. Okay, so in this slide I will show you how you're going to transform the NB node here in terms of theta. Okay, so for this part of component A, I think you are clear with this. Okay, let's see for component B. Okay, so as we know, theta B will equal to the NB node over with the NA node. Okay, so if you can see, this is NB node. So NB node is equals to theta B times with the NA node. Okay, so this one you will replace it with the theta B times with the NA node. Okay, so let me expand the equation. You will have a theta B NA node, alright, minus with the B over A NA node X over with the V. Okay, so if you can see, there's an NA node X and this is NA node X. Okay, so you can take it out and then put it in the left side. Okay, and then this one times with the theta B minus with the B over A times with the N, sorry, no need N, but you already put it here, so times with the X over with the V. Okay, so automatically this one you can change it into the CA node. Okay, so for the C1, okay, I do it again. Okay, I show you again one by one how to transform to the theta, what do you call it, theta C. Okay, alright, so theta C, okay, this is for C, okay, to theta C. Okay, so theta C is equals to NC naught over with the NA naught. Alright, so even though NC naught is 0, but we just express it in algebraic. Alright, so that we need to convert the N into the concentration. Okay, so NC naught is equals to, alright, NA naught times with the theta C. Okay, so if you can see, this is NC naught. Okay, this is NC naught. Okay, so you can equate it to N theta C and A naught. Okay, so this equation would become, okay, you have a new equation, which is the NC, what do you call it, NA naught, alright, times with the delta C, alright, plus with the C over A, alright, and NA naught X, alright, over with the V. Alright, so you just put in one side NA naught, alright, and then we have a theta C plus with the C over A, alright, times with the X over with the V. Alright, so that's why this one will become CA naught. Okay, we want to standardize this one will become CA naught. Okay, this one also repeat. Okay, so theta D is equal to ND naught over NA naught. Alright, so this one ND naught equals to theta D times with the NA naught. Alright, so just replace this one and then simplify it. Okay, so at the end, what you will get is in terms of CA naught for each of the component here. Okay, so this one would be CA naught is equals to NA naught over with the V naught. Okay, same as this one. Okay, remember this one represent with the theta C, this one is the theta B, and this one is the theta D. Alright, this is the final equation for the concentration terms. Okay, so let's say there is an equation for the red loop, which is negative RA, is equal to KCA times with the CB. Okay, so what is CA? CA is this one, which is CA naught times the 1 minus X, and then we times it with the CB, which is this one. Alright, times with the CA naught, okay, theta B minus B over AX. Alright, this one we can make it a CS naught squared. Alright, times with 1 minus X times with the theta B minus BA. Okay, alright, hopefully this clears you. Alright, okay, so let us look at the example 3-2, liquid phase reaction. Okay, so the liquid reaction involve the sodium hydroxide plus with glycerol stearate. Okay, to form a sodium stearate and glycerin. Okay, so let denote this one as a A. Alright, plus with the B is equals to 3C plus with the D. So you translate the previous equation with the molecular formula into species A, B, C and D. Alright, then now his sodium hydroxide will become the limiting reactant. Alright, so the stochometric equation here, alright, need to be divided with B, C and D. Alright, that's why you have A plus 1 over 3B is equal to C plus with the 1 over 3D. Okay, so what you have to do is you need to construct the Stochometric table, okay, and then get the final concentration equation for each of the molecules. Okay, so for example, this is the definition that we want, which is the Ca is equal to Na over V. Alright, so since this is a batch system, so V will equals to V naught. Okay, so from here we have a Na over V naught. Okay, sebab apa kita nak V naught? Sebab sebenarnya kita nak transfer Ca ni daripada Na naught over V naught. Okay, so this one, what is Na? Is Na naught times with 1 minus X over V naught. Okay, ni yang the one yang buat lah, minus Na naught X. Okay, so you will be able to get Ca naught times with 1 minus X. Okay, and don't forget the theta B, theta C and theta D. Alright, just put it as a species here now and so on, and then the symbol A, B, C, D and I. Okay, so the water will act as an inert. Okay, and this is the initial value for the at T equals to 0. We have Na naught and B naught and C naught and D naught and also Ni naught. Okay, for the change we have for the A is minus Na naught times X, and for the change for the B is minus 1 over 3 times Na naught X, and for the C is Na naught X, and for the D is 1 over 3 Na naught X. Okay, and then remember for the inert there is no change happen. Okay, there's no reaction happen, so this should be 0 lah. Alright, and then we have a remaining, okay, which is you have to remaining is equals to initially plus with the change. Alright, then you will be able to get this column lah. Okay, so from here, alright, how do you get the Ca naught? This one need to be divided with the V naught here. Okay, so that's why you will have this one. Okay, Ca naught semua ni lah. Alright, okay. So for example 3-3, okay, this relate with this previous example. You need to get the concentration of glycerin, which is D, when the conversion of sodium hydroxide, okay, which is A, is 20% and 90%. So it is given the value of X, Alright, okay, and also the question give you the value for the CA0 initial mixture consists of A, alright, which is 10 mole over decimeter cube, and also glycerol stearate, which is the B, alright, CB0 equals to 2 mole over decimeter cube. Okay, so you need to get what is the concentration of the CD. Okay, so you just actually use what you call it, the formula from the Stochometric table that you obtain, alright, to get the CD. Okay, so for the conversion of the 20%, which is 0.2. Okay, so what is the CD? So CD is equals to CA0 times with the theta D plus with the X over with the 3. Okay, so theta D, we can make it as 0 because theta D is equals to N D naught over N A naught. Okay, there's no value for D at D0. Okay, so we can cancel it here. Okay, so you just put it as CA0, which is 10 mole over decimeter cube times with the 0.2 divided by 3. Okay, so you will get the answer here. Okay, so same formula used for the X equal to 0.9. Okay, to get the CD. Alright. Okay, now we move into the batch vector with variable volume. Okay, so before this, you learn about the batch vector with constant volume. Okay, now it is a variable volume. Okay, means that there is a change in the volume. Okay, so individual concentration can be determined by expressing the volume V for batch system or volumetric flow rate V. Okay, if you have a small letter here, means that for a flow system. Okay, don't get confused. V capital is for volume, and the small letter would be volumetric flow rate. Okay, so this one usually we use for batch lah, for N number of moles. Okay, this one we have for F flow. Okay, alright, so as a function of conversion using the following equation of state. Okay, this is the one that you learn in thermodynamic, whereby we have PV is equal to Z NT over RT. Okay, remember as I told you, for the constant volume it should be incompressible, alright, system. But for the variable volume, we will consider compressibility, okay, factor. So PV is equal to Z NT times R times T. Okay, so the unit of the T and the P is depending on the R. Okay, so from here you can try to transform into at T equals to 0. So you need to put 0 here. Right, P naught V naught is equal to Z naught NT naught RT naught. Okay, so you can equate it. Alright, like PV, okay, over with the P naught V naught is equals to Z NT RT. Okay, so this one is at any T. Okay, right, so over with the Z naught and T naught RT naught. Okay, so you arrange it to make it as V at the left side. So V is equal to this one. Okay, so now what I'm going to explain to you how we want to simplify the NT over NT naught. Okay, so this is, remember, this is for variable volume. Okay, so for variable volume, if you can remember, at the last chapter of topic number 2, there is a term of 1 plus epsilon x. Okay, so this one actually will be applied for this. Okay, so have a look first. This is the mind map, okay, to categorize between batch and flow system. Okay, so I will recommend you to do a mind map. Okay, so that you won't get confused with the terms. Alright. Okay, so for the liquid phase, it is incompressible. We have a batch system and flow system. Okay, so usually flow system is for CSTR and PFR. For batch system, we can operate in CSTR as a batch mode operation. Okay, so the volume would be the same, and the volumetric flow rate, alright, the small v would be the same. Okay, so this one we have a PV is equal to nRT. Okay. For liquid, volume change with reaction is negligible because there's no phase changes are taking place. Okay, they tak convert into another phase, into a gas ke, liquid ke, and so on. Okay, so for gas phase, we have two different category, which is in terms of constant volume here. Another one is the variable volume. Okay, so for the constant volume is the same, which is the V is equal to V naught, and here volumetric flow rate is equal to volumetric flow rate naught, alright, at T0. And then for variable volume, we have a batch as well as the flow. Okay, so for the batch, you will use this equation, and for the flow, this is the equation. Okay, so don't worry, I will explain one by one. Okay, after this. Alright, so let's say we have a total number of mole for the system denoted with the NT. Alright, so the NT is equal to NT naught plus del NA naught times with the X. Okay, this is a similar like a batch before juga as for the constant volume, remember? Okay, whereby del here, if you still remember, represent with this equation. Okay, still the same like constant volume. Okay, it's just that there is a new term which is the epsilon. Okay, so you need to remember NT over NT naught. Okay, okay, daripada mana kita dapat NT over NT naught, remember is from the previous slide. This one, V is equal to V naught, P naught over P, alright, and then we have T over T naught, alright, times with the Z over Z naught, alright, times with the NT over with the NT naught here. Okay, so this one actually NT over NT naught is 1 plus E epsilon X. Okay, so from here, we want to divide it with the NT naught for each of the value here. So you will have NT over NT naught over NT naught here, and this one is over NT naught. Okay, so this is the one. Alright, NT over NT naught equals to 1. This one divided become 1. Okay, plus with NA naught over NT naught here. Okay, remember kita dah divide with NT naught. Okay, times with the del and X here. Okay, so we have a new definition, which is the y a naught is equals to the fraction of the n a naught over n t naught. Alright, so this is the fraction. Okay, so you can simplify it. Alright, and then it becomes 1 equals to 1 plus del x, and this one times with the y a naught. Okay, so this one can replace with the 1 plus epsilon x. Okay, because of what? Epsilon is equals to del times y a naught. Okay, so apa yang you kena ingat adalah what is nt over nt naught, which is 1 plus epsilon x. Alright, and then what is y a naught? Alright, so y a naught is equals to n a naught over nt naught, and what is epsilon? So what epsilon is equals to del times with the y a naught. Okay, kena ingat benda ni. Okay, so this one I don't have to explain lah sebab ni sama macam previous one. Okay. Alright, so equation 3-34, alright, is further simplified by letting, alright, epsilon is equals to, this one is del, okay, and this one is YA0. Alright, so you will have epsilon is equals to YA0, alright, del. Okay, so NT over NT0 is equal to 1 plus epsilon x, means that 1 plus with the del YA0 times with the x. Okay, alright, so epsilon is defined as the change in the total number of moles for complete conversions, okay, divided by the total number of mole fed to the reactor. Okay, this one. Okay, so for the equation 3-32, it can be simplified because the Z, we assume it will be approximately equal to Z0, okay, for the real volume over with the ideal volume. Okay, so this one you can cancel as 1. Okay, so this is the remaining one lah. And V0, P0 over P, T over T0, and then 1 plus epsilon x. Okay, alright, so remember NT over NT0 is equals to 1 plus epsilon x. Alright, okay, we move into the next slide. Okay, so in the gas phase system that we shall be studying, the temperature and pressure are such that the compressibility factor will not change significantly during the course of the reaction. Hence, Z0 is equal to Z. Okay, so that's why we already cancelled the Z terms. For a batch system, the volume of the gas at any time t is defined as this one. Okay, so this is a batch system. Alright. Okay, so we have a V equal to V0, P0 over P, 1 plus EX, T over T0. Okay, so this one actually is coming from the previous one lah, which is the NT over NT0. Okay, so equation 3-38 applies only to a variable volume batch reactor. Okay, remember this is for variable volume. Okay, sebab kalau untuk constant gas phase volume should be V is equal to V0 and then ni equals to V0. Okay, dia tak ada extra yang ni. Okay, so if the reactor is a rigid steel container of constant volume, then of course V is equal to V0. For a constant container, V is equal to V0. And equation 3-38 can be used to calculate the pressure inside the reactor as a function of temperature and conversion. Okay, means that kalau kita ada constant volume, okay, of course the pressure inside the reactor dia tak berubah. Okay, so you can get to calculate the pressure inside lah. Alright. Okay, so for example, this kind of equation. Okay, we have a gas phase reaction take place in the 1.5 decimeter cube, which is the volume, at temperature of 75 degrees and the pressure of the 2 atm. Alright, so it's given this formula, this reaction, which is a 3A is equal to B plus 2C. Okay, so from here actually we have to construct a Stochometric table of the system and express the concentration of A, B and C as a function of conversion X for a constant pressure isothermal batch reactor. Okay, so when there is a word of constant pressure isothermal batch reactor, means that we have a V is equals to V0 times 1 plus epsilon X. Alright, okay, times with the P over P0, T0 over T. Okay, so when it's a constant pressure isothermal batch reactor, means that you need to use this equation. Okay, in terms of the ni lah V. Okay, so this one you can cancel lah sebab it's a constant pressure and it's isothermal. Okay, ni lah yang you akan guna. Okay, so you have to construct the table lah. This one lepas ni you akan belajar more details. Okay, alright. Okay, this is for the flow system. Okay, just now kita untuk untuk batch system, sekarang flow system. Okay, flow system dia ada juga variable and variable volume and also constant volume. Okay, jangan confuse, tengok balik pada mind map tadi. Okay, so let's say we have a reaction here. Okay, macam PFR lah ni, a long cylindrical tube. Okay, there is a entering what do you call it, from A, B, C, D and I species. Alright, and this is the reaction equation. Okay, and there is a leaving, which is the effluent ataupun outlet. Okay, after a certain time. Okay, so this would be T is equal to 0. Alright, this one is the T at any time lah. Okay, so this one would be the F total naught, and this one would be the FT, the total. Okay, so always remember what is F. Alright, F is equals to N over T, which is in terms of mole over time. Okay, it can be in second or minute or hours. Okay, depending. Okay, so how we relate with the concentration? So CA is equal to FA over V. This is V, small v, okay, not the capital V, not the volume. Okay, this is volumetric flow rate, which is the FA has the unit of moles over time, and for the volumetric flow rate is the liters or decimeter cube over time. Okay, so at the end you will get the unit, the concentration, the unit of concentration, moles per liter. Okay. Alright, so now what you need to do is you need to simplify the equation. Okay, remember we have a theta that you've learned before. As I mentioned to you, theta can be in terms of the F, C or Y. Okay, so you just need to adjust it. Okay, for example, we have a theta B would equals to FB naught over with the FA naught. Alright, so this one is equals to I. Sekarang kita convert to the species B, which is CB naught. Alright, over CA naught. Okay, why we have to times with the V naught? Sebab F is equals to, alright, C times with the volumetric flow rate. Okay, so we have V naught here and we have a V naught here. Okay, so here we can cancel the V naught. Alright, sebab this is the constant volumetric flow rate in the batch. Okay, so we have CB naught over CA naught. Okay, alright. Okay, kalau senang nak tahu, Fi is equals to CIV. Okay, for Fi naught is equals to CI naught times with the V naught. Okay. Okay, for the batch system and the flow system. Okay, batch system versus with the flow system. Okay, same equation. We have A and plus B reactant to form C and D product. Okay, so the batch one is the one that you dah belajar previously, and then for the flow system, okay, this is a new term. Alright, F and also small letter of V. Okay, so from here actually what we need to do is to convert this into a CA naught. Alright, same as for the batch system. Okay, so this one also we want to change into CA naught. Okay, but if we want to change it, we need to simplify it into theta first. Okay, for example, for B here. Okay, so CB is equal to FB over the volumetric flow rate. Alright, is equals to, remember, theta B is equals to FB naught over with the FA naught. Alright, so here we have FB naught, so FB naught will equals to theta B times with the FA naught. Okay, so here hopefully you can see my small ni words here, theta B times with the FA naught, alright, minus with the B over A times with the FA naught X over with the volumetric flow rate. Okay, so this one you can take it out, alright, make it F A naught, alright, times with the theta B, okay, minus with the B over A X, and then over with the V. Alright, so this one you can change it into C A naught. Alright, hopefully you understand this part. Alright, so how we get this one? Okay, so if V is equals to V naught, alright, this is a constant, alright, constant of volumetric flow rate. Then we have a CA is equal to FA over volumetric flow rate is equal to FA naught 1 minus X over with the volumetric flow rate. So you just cancel this one, becomes CA naught 1 times minus X. Okay, but if V is not equals to V naught, then you will have, okay, CA is equal to same FAV. Alright, it's just that dalam ni akan berbeza, which is FA naught times with the 1 minus X, alright, over with the V naught 1 plus EX. Okay, sebab bila ada variable volume, it becomes V ni akan equals to V naught 1 plus epsilon X. Okay, nanti kita akan ni lah, learn more. Allah, bunyi cicak lah pula. Tak maaf lah saya buat apa video ni tengah pagi sebab tengah tunggu my kids sleep dulu baru I boleh record. Okay, alright, so this one is kalau you nak buat ni lah sama je lebih kurang. Okay, so for the next slide we have Stochometric table for a flow system. Okay, let us do one by one. Okay, so effluent rate would be equals to feed rate plus with change. Okay, so this one, okay, this one I think you dah clear enough. Okay, for B, alright, we have a change of B times with this one, so it will become FB is equals to FB naught over with the B over A FA naught X. Okay, so kalau you nak change this one into theta, so dia akan jadi theta B is equal to FB naught over with the FA naught, means that FB naught is equal to theta B times with the FA naught. Okay, so this one would be theta B times with the FA naught, alright, minus with the B over A FA naught times with the X. Okay, so this is the equation lah. And then for C, this one, for C, FC naught is equal to theta C, okay, times with the FA naught, alright, and then this one is C over A times with the FA naught X, right, and then this would become FC, alright, is equals to FC naught plus with the C over A times with the FA naught X. Okay, remember you dah change this one, so it comes theta C FA naught minus over B this one FA naught times with the X. Okay, so this one same also. We have a FD naught is equal to theta D FA naught. Okay, ini D naught, sorry. Okay, and then plus with the D over A FA naught X. Okay, so FD will equals to initial plus with the change, which is FD naught plus with the C D over A FA naught X equals to theta D FA naught plus, sorry, this should be plus, oh, this is C, sorry, dah malam kan. Okay, over plus D over A times FA naught times X. Okay, so this will represent the FT naught, which equals to FA naught plus FB naught plus FC naught plus D naught, and this will represent the FT, which is FT is equal to FA plus FB plus FC, alright, plus with the FT. Okay, so you see, keluarkan macam ni lah, as this one. Okay, so we move on to flow reactor with variable volumetric flow rate. Okay, just now is for constant volumetric flow rate. Okay, sekarang ni variable volumetric flow rate. Okay, kita still in flow system. Okay, so to derive the concentration of the species, okay, lupa cakap ini for gas phase. Okay, jangan keliru. Okay, so to derive the concentration of the species in terms of conversion for a variable volume flow system, we shall use the relationship for the total concentration. Okay, so the total concentration at any point in the reactor is, so at any t, it becomes Ct is equal to Ft over volumetric flow rate is equals to P over Z RT. Okay, macam mana you dapat ni? Sebab kita dapat we have PV is equal to nRT. Okay, so when you have N divided with V, alright, this one would become concentration. Okay, that's why N over V is equal to C is equals to P over ZRT lah. Ni kalau ada letak Z lah. Okay, so this is for the T, total concentration, and then at the entrance of the reactor we have T equal to 0. It should be like this. Okay, just letak je 0 kat sini lah. Okay, alright, sini 0 ni tak ada, ni R. Okay, so taking equation 3-40 dengan 3-39 and assume that Z is approximately same as Z0, so you can cancel. Alright, so the final equation would be like this. Alright, 3, 4, 1. Okay, alright. Okay, so from here we have a Ft is equal to Ft0 plus Fa0 del X. Okay, you akan tengok dekat sini. So daripada situ, remember what is del? So del should be D over A plus with the C over A minus B over A minus 1. Okay, so we expand the equation. Alright, so this one actually is referring to Ft over Ft0. Macam mana kita dapat ni? By dividing all this equation 343 with Ft0. So this one you divide, this one you divide, and this one you divide. Okay, so that's why you jadi macam ni. Okay, so then okay, ni yang untuknya. Alright, so from here you can simplify, dah akan jadi ni lah. Sebab sini ni yang ni jadi 1. So 1 plus Fa0 ni dot ni. Alright, and then you can replace it the Fa0 over Ft0. Okay, in term of fraction. So we have remember Fa0 over Ft0 is equals to Ya0. Alright, this is a mole fraction of A. Mole fraction of A. Okay, so here you just replace it with Ya0. Okay, so it become like this. Alright, so remember what is epsilon? Guys, suruh ingat 3 benda yang tadi. So epsilon is equals to del times with the Ya0. Alright, so this one you can replace it with epsilon. Alright, at the end you will get this final equation. Alright, okay, ni untuk variable volume. Okay, so from here, okay, remember we have a Cj is equal to Fj over V. Alright, macam mana kita dapat this equation? Actually is referring to the previous what do you call it? Mana tak boleh nak buka previous punya ni lah, yang kita dapat V is equal to V0. Alright, times with the Ft over Ft0, P0 over Pt over T0. Okay, so daripada sini you bawa ni atas dia, so terjadilah this equation. Okay, so daripada sini we have a Cj is equal to Ct0. Alright, kenapa kita dapat Ct0? Sebab from this one. Okay, remember what is the definition of concentration in terms of F, which is C is equal to F over volumetric flow rate. Okay, in this case, which is TTO is equals to FTO over with the volumetric rate at T0. Okay, so just replace this one with CT0, then you will have this equation. Okay, my explanation clarify you. Okay, and then we have a substitute for V, volumetric flow rate, using equation 3-42 for Fj, we have this one. Okay, so from here, alright, we represent this one with a stochometric coefficient. Alright, the Vj here. Okay, this is a theta. Alright, okay, over with the V0 1 plus Ex P0 over Pt over T0. Okay, for example, okay, let's say if we choose B for the CB lah. So CB is equals to FB, alright, over with the V, alright. Okay, so from here is equals to what is FD? Okay, FB ni sebenarnya you dapat daripada Stochometric Table, which is FA0, okay, times with the theta B. Ikut dia benda ni, cuma you ubah J tu lah, minus with the VJ ni berdasarkan pada you akan ubah ni dengan ubah yang ni tau. Alright, so minus with the B over A, alright, times with the X over, remember V is equal to V0 times with 1 plus epsilon X, okay, and P0 over P times with the T over T0. Okay, so macam tu lah you buat. Okay, contoh lagi satu lah nak bagi clear lagi. Let's say kalau you nak dalam in term of C pula, C as a product, so just put it as CD, sinilah nampak sikit, CD is equals to FD over dengan ni, alright, volumetric flow rate is equals to what is FD, which is FA0 times with theta D plus with the VJ kan. So VJ untuk produk kena positif. So D over A times with the X over with the V0 1 plus epsilon X P0 over P times with T over T0. Okay, itulah cara you dapat. Alright. So how do you get the CA0 here? Actually is by dividing FA0 with V0 here. Okay, so this would be the CA0. So dah akan jadi macam ni lah. Alright. Okay, so this is a table 3-5 summary, alright, of the previous one. Okay, this is for the variable volume gas flow. Okay, that's why kita ada V is equal to V0 1 plus epsilon X times with the T0 over T P over P0. Okay, kalau dia constant, dia tak akan ada 1 plus EX ni lah, tapi still ada ni lah untuk gas. Okay, yang ni. Alright, so ini dia punya summary lah. Alright, ni I don't have to explain lah lagi. Okay, now we move into the flow system. Alright, this is for liquid system, phase system. Okay, sebelum ni kita untuk liquid phase system, untuk batch system, which is V besar is equal to this one kan, mana saya punya ni, V is equal to V0. Okay, sebelum ni kita focus on the batch system, liquid. Okay, tapi sekarang flow system pula. Alright, for liquid phase system, the concentration for flow can be calculated as, okay, sama juga, CA is equal to FA over volumetric flow rate. Okay, so this is a liquid phase flow system with constant volumetric flow rate. Okay, sebelum ni kita belajar batch with the constant volume. Okay, this one is flow tapi untuk constant volumetric flow rate. Okay, so we have a CAFA over V. So this one just FA0 1 minus X over V0. Okay, so this one is a CA0 times 1 minus x. Okay, then how we get the b actually is equal to fb over v. Alright, so is equals to f a naught. Alright, remember this one is from the Stochometric Table. Alright, theta b will minus b over a times x over v naught. Okay, so this one we can get it as c a naught. Okay, so negative rk ca cb. Okay, so this one would be the ca and this one would be the cb. Okay, so you just simplify, you can get this equation. Alright, okay, so recall back. Okay, for liquid phase we have a flow and we have a batch. Okay, this is for CB is equal to FB over V. Alright, if there is no phase change, the volumetric flow rate will not be changed. There's no difference between t equals to 0 and at any time. And for batch, there's no changes in the volume. Alright, but if you can see, flow is in terms of FB over V, and this one is NB over, actually this should be V capital. Okay, and then this is how you get the concentration. Okay, you're gonna tengok balik lah. Alright, and this one gas phase, if you can see, kita ada batch juga for constant volume. Okay, it's just that for batch kita ada ni lah different, which is kita ada P dengan T. Okay, terms ni, this one also. Okay, so kalau you tengok batch, dia akan refer to volume. Okay, kalau flow, volumetric flow rate, kita akan refer to the ni lah flow. Sorry, flow akan refer to volumetric flow rate. Sekejap Okay, so don't get confused. Okay, for gas phase, it also has a constant, what do you call it? Constant volume and constant volumetric flow rate. Okay, so this would be the equation. Okay, but for variable volume, so we have this one. Okay, which is 1 plus epsilon x. Okay, and this one we already learned before this. And if there is no pressure drop, and if it's isothermal, so you can cancel this part. But if there is no pressure drop and also it is isothermal, so you can cancel these two terms. Okay, and becoming this one. So this one is for the gas phase. Okay, remember we have epsilon is equal to ya naught times del. And then we have a CT naught is equal to P naught over RT naught. Okay, so CA naught, you can make it as a CA naught, alright, which is the by changing with the YA naught, alright, because YA naught is equals to CA naught over CT naught, alright. So the concentration of the gas will be different depending on the composition of the gas lah. Okay, let's do some exercise. So then this question is about the gas phase reaction is below is carried out isothermally and in a tubular flow reactor. The reactors are fed at a ratio of 30% A and 70% B to the reactor at a constant pressure of 17 atm and at temperature of 250 degrees Celsius. So it is given, this is the equations. Okay, so if you can see, this is a gas phase reaction. Okay, and this carried out isothermally, means that T is equal to T naught, alright, in a tubular flow reactor. So it should be in a flow system. So this is a variable volume, okay, which you need to consider. V is equal to V naught 1 plus epsilon x. Okay, so from here you have to construct a complete stoichiometric table that shows each species leaving the reactor. Take A as the limiting reactant. Okay, so A would be the limiting reactant. Okay, And B, we have to determine the concentration of C. Alright, what is the C? Alright, when X is 85%. Okay, so first, for this first exercise, I will show the solution. Alright, so let me try to get the answer for A. So you have to tabulate, you have to make a table, which is the first column would be the species, and then we have the second column, which is the initial. Alright, and then we have a change here, and then we have a leaving here. Okay, so this one species denoted with A, B, and C. Alright, this would be F A naught, F B naught, and this one is F C naught. Alright, for this one we have, okay, this is A is equal plus with the 2 divided by 3B equals to 1 over 3C. Okay, so here it should become minus F A naught X over with the minus 2 over 3 F A naught X, and then we have 1 plus here over 3 F A naught X. Alright, so the leaving species would be CA is equals to, remember this one is one flow, so F A naught should be over with the, this is variable volume, V naught, times with the 1 over epsilon X, this one 1 minus X. Okay, alright, sebab asalnya lah CA is equal to FA over dengan V. Okay, so dari sini kita dapat FA naught, alright, which is 1 minus X over with V naught 1 plus epsilon X. Okay, macam yang ni lah. Okay, then the B should be CB is equal to F A naught. Alright, and you have a X here, which is 2 over 3. Okay, alamak, tak muat main buat ni. This one is theta B. Alright, minus with the 2 over 3x, alright, over with the V naught 1 plus EX. Okay, so it becomes CA naught theta B minus 2 over 3x over with the 1 plus epsilon X. Okay, so for CC, sorry, I kena buat kat sini tak muat, is equals to, okay, is equals to FC over ni is equals to FA naught times with the theta C, alright, plus with 1 over 3x over with the V naught times 1 plus epsilon X. So this one kita boleh jadikan CA naught. Alright, okay, for the B part, okay, sorry, kenapa tak boleh ni? I'm not sure kenapa tak boleh. So untuk B part, I have to stop sekejap.